Hello all, in this lesson we're going to be studying oxidation states, and our aim is what is an oxidation state, or what is an oxidation number. The homework associated with this lesson is 1 through 10 on pages 160 to 161. We'll work on that in class tomorrow. And your do now is very simple. Distinguish between oxidation and reduction. Don't answer it yet, we'll do that in class tomorrow. So for the last couple of days we've been talking about oxidation and reduction. And when you look at a formula or an equation, it's not always possible to tell if electrons have been moved back and forth. So it's not always possible to immediately tell if oxidation or reduction has occurred. But in this lesson, we're going to figure out all the ways that we can figure out for sure if oxidation and reduction has occurred, even if it's not obvious. So it starts with a conversation about charges versus oxidation states. So all year long, we've been putting those little numbers with pluses and minuses beside atoms' symbols, and we've been calling them charges. But you can also think of them as oxidation numbers or oxidation states. And an oxidation state, by definition, just tells you how many electrons have been lost or gained by a substance. So for instance, if you have a charge of 2 plus or plus 2, that means that you have lost 2 electrons. So depending on whether I am asking you about a charge or an oxidation state, you might say 2 plus, or perhaps you would say plus 2. So those are two different ideas. The 2 plus is if I ask you for the charge of an atom, and the plus 2 is when I ask you for the oxidation state. The reasoning for that is based on a number line. So we always start our atoms at neutral. So let's say that this is neutral. But then let's say that an atom loses 2 electrons. In order to understand that, we can start numbering our number line just like we would in math class. So let's say that the atom loses 2 electrons, right? So it's going to go from 0 to 1 to 2 as its charge. And you would definitely say a positive 2 as the oxidation state because that is reflecting the math on the number line. So if an element gains 2 electrons, it would be basically the opposite. So it would go from here to there, which would be a negative 2. So when an element gains 2 electrons, its oxidation number is negative 2, and its ion charge, or its charge, would be 2 minus. All right, so when we're looking inside a compound and we need to know how to assign actual oxidation numbers to individual elements, we're going to need the rules on the next page. So these rules are not on your reference table, and you need to know every one of them. So you're going to have a lot of memorization to do for this lesson, but for now, basically, whenever you see like number 1, number 2, number 3, you have to have that rule copied down. I would suggest verbatim, or really think about it before you put it in your own words. Okay, I'll walk you through each example. Number 1, let's say that each uncombined element has an oxidation number of 0. So for instance, sodium is an uncombined element in this example, so it's going to have an oxidation number of 0. And even chlorine is an uncombined element. Even though it says Cl2, it's uncombined with another element, so its oxidation number is still going to be 0. So 0 for the oxidation number of sodium and 0 for the oxidation number of chlorine. Here's an example. A student answers that the oxidation number of the nitrogen in N2 is negative 1. Let's revise her work. Well, nitrogen in N2 is, this is considered an uncombined element. And that's because it isn't combined with any other elements. So if it's uncombined, then it has to have an oxidation number of 0. Next example. Monatomic ions have an oxidation number equal to the ionic charge. This is very fancy language, but it's basically telling you that an ion's charge is equal to its oxidation number. So for instance, they're talking about, like in this equation, like when you look at the NaCl, we know that the sodium ion has a 1 plus charge, and we know that the chloride ion has a 1- charge. And that would mean that the oxidation state is equal to that number, but instead of saying 1+, you'd say +1, and instead of saying 1-, you'd say -1. Let's try this example together. A student answers that the oxidation number of calcium in calcium oxide is +1 based on the subscript of the oxygen. So the oxygen was a subscript of 1, so she's thinking that we'll need a +1 for the calcium. While her work is not entirely misguided, calcium and oxygen are actually both have a charge of 2. Calcium is +2 and oxygen is -2. So the oxidation number of calcium is +2. Number 3. The metals of group 1 always have an oxidation number of +1 if it's in a compound. And the metals of group 2 always have an oxidation number of +2 if they're in compounds. As examples, sodium has an oxidation number of +1 in sodium chloride, so that sodium has a +1 oxidation number. And magnesium always has an oxidation number of +2 in magnesium oxide, so that particular magnesium is a +2 oxidation number. Let's do an example together. A student answers that the oxidation number of lithium in lithium chloride is 0, revise her work. So I'm not really sure where she would get the 0 from, but I can tell you that lithium is in group 1, so it's always going to have a charge of +1. Number 4. Fluorine is always -1 in compounds. The other halogens are also -1 when they are the most electronegative element in the compound. So I'll write down the elements that are considered halogens right here to the left in order from top to bottom. So here's the list. It goes from fluorine, chlorine, bromine, iodine, astatine, and basically this rule is telling you that fluorine is always -1 with no exceptions, and chlorine would be -1 as long as it's the most electronegative element in that compound. Same thing for bromine, iodine, and astatine. Obviously, if chlorine is bonded to fluorine, then fluorine is -1 and chlorine would be +1. Okay, so here are my examples. Fluorine has an oxidation number of -1 in HF, so that's not an exception. It's always going to be -1. Same thing here, NaF, same thing here, LiF. Now the other halogens will follow suit, but like in HCl, that'll be a -1 for the chlorine because it's a halogen. NaCl, yeah, and LiCl, same thing. Here are some examples for us to work on. So let's say that a student says that the oxidation number of F in OF2 is a -2. Let's revise our work. Well, since fluorine is always -1 with no exceptions, then we would just need to say -1. Secondly, a student answers that the oxidation number of fluorine in NaF is 0, revise our work. Well, fluorine is always -1, so -1 again. Thirdly, a student answers that the oxidation number of iodine in sodium iodide is 0. So basically, iodine is group 17, it's a halogen. And that means it's almost always going to be -1 as long as it's the most electronegative element in the compound. And iodine is more electronegative than sodium. So my answer for iodine there is going to be -1. Now, the last example on this page, we have a student answers that the oxidation number of iodine in iodine fluoride is -1, revise her work. So fluorine is always -1, which means iodine in this case needs to be +1 in order for the compound to stay neutral. So we're going to have to say +1 for iodine in that case. Rule number 5 says that hydrogen is +1 in compounds unless it's combined with a metal, in which case it is -1. So for instance, hydrogen is +1 in HCl, but it would be -1 in LiH because lithium, the metal, is going to be +1. Let's do a couple more examples. A student answers that the oxidation number of H in HF is -1. Well, when the H is written first, you can think of it as +1. Additionally, the fluorine is always -1. So in that case, the hydrogen has to be +1. Additionally, a student answers that the oxidation number of hydrogen in sodium hydride is +1. So hydrogen is usually +1, but if it's bonded to a metal, the metal has to be +1, in which case the hydrogen would be -1. Number 6, oxygen is usually -2, but if it is combined with fluorine, it would have to be more electronegative, the fluorine, so oxygen would be +2 in that case. And additionally, if the oxygen is inside a peroxide ion, it's -1. Here are the examples for that. So oxygen is -2 in water. This case is what I would consider normal. But it's +2 in OF2, and that's because the oxygen is +2, whereas the fluorines are -1. So 2 times -1 is -2, and the oxygen would have to be +2. And then lastly, in the peroxide ion, which is this guy, oxygen is going to be -1 because you need to have 2 of them, which is this 2, to add up to a total of -2. Here are some examples. A student answers that the oxidation number of oxygen in OF2 is -2. Revise her work. Well, the fluorine is going to be -1, which means that the oxygen would have to be +2. Secondly, a student answers that the oxidation number of oxygen in CO2 is +2. Revise her work. So oxygen is almost always -2, and this is the case in this example. And then thirdly, a student answers that the oxidation number of oxygen in H2O2 is -2. So close, the peroxide ion itself is -2, but each of the oxygen atoms is going to be -1. So rule number 7 tells me that when I add all of the oxidation numbers in a compound together, that it has to be equal to 0. Here's an example using HNO3. So the hydrogens are almost always +1. And nitrogens, we don't know their oxidation number. I haven't listed any rules yet. I have said that oxygens are almost always -2, barring certain circumstances. So when you do the -2 times the 3 for the oxygen, meaning that there's 3 atoms whose charge is -2, you're going to get an overall charge of -6. And for the hydrogen, there's only 1 of them, so the overall charge is +1. And when you take the charge of the nitrogen and add it to the +1 and the -6, it has to be equal to 0. That's what rule number 7 is saying. So +1 for hydrogen, plus N, whatever that is, -6 has to be equal to 0. So when you do that math, you'll see that nitrogen has to be equal to +5. So that's why I'm going to say that the oxidation number of nitrogen is +5 in that circumstance. Let's do another example. A student answers that the sum of the oxidation numbers in CO2 is -8. Obviously, CO2 is a compound, and all compounds have to have an oxidation sum of 0. Secondly, a student answers that the oxidation number of nitrogen in NO2 is -3. While some nitrogens would have an oxidation number of -3, it's not every nitrogen, so let's do an example. So oxygen is definitely -2. -2 times 2 is -4. And the nitrogen, when added to the -4, is going to have to equal 0. So in this case, the nitrogen has to be +4. So +4 is my answer. And in rule number 8, it says that the sum of the oxidation numbers in a polyatomic ion has to be equal to the charge of the ion, not 0. So for instance, if you take a look at the dichromate ion, oxygens are an oxidation number of -2 overall, and then -2 times 7 is going to give me a -14 for the oxygens. So I'll just keep track down here. But that has to be added to the charge of the chromium. Now, there are 2 chromiums, and I'm not sure how much each one of them has for its oxidation number, so I'll just write 2Cr. So there's 2 chromiums, and a negative 14 for the 7 oxygens. And they have to be equal to the charge of the ion, which is listed up here as negative 2. So 2Cr minus 14 is negative 2. Let me do some algebra on this. I can condense this to say 2Cr is equal to positive 12. I added 14 to both sides. And then Cr itself would have to be equal to positive 6. So that's how I get the positive 6 as my answer. And then my last example for this lesson is a student answers that the oxidation number of sulfur in the sulfate ion is negative 2. Revise her work. So the sulfate ion has an overall charge of negative 2. So when I add all these together, it's going to be equal to negative 2. The sulfur I'm not sure about, but oxygen is definitely negative 2 in this case, but it's negative 2 times 4. So let's go negative 8. That means that the sulfur has to be, we'll add 8 to both sides, and the sulfur has to be positive 6. So that was my last example for this lesson. I hope that you learned something about oxidation numbers and how to assign them, and we'll be working on bookwork in class tomorrow. Thanks for watching.